In this video, we will try to solve a question on constrained optimization. The question is, if the production function is given as q is equal to k to the power 0.5 l to the power 0.5, where q is the quantity produced and k and l are the inputs of capital and labor respectively, such that the budget constraint is given as, that is 8 times the capital plus 4 times the number of labor hours is equal to 368. We have to find the level of capital and labor that maximizes utility. Okay, so these questions can be solved using the Lagrange's multiplier method. First of all, we write this very given production function, that is q is equal to k to the power 0.5 l to the power 0.5, and it is called objective function. Okay, and we are given the budget constraint, so such that 8 times capital plus 4 times the labor is equal to 368. We have to maximize this very production function subject to the budget constraint. Okay, so this is called the constraint function. Okay, first step is we set this constraint function equal to 0. Okay, which will imply that 368 minus 8k minus 4l is equal to 0. Okay, first step is setting constant equal to 0. Next step is multiplying this very constant by lambda. Okay, these are the two important steps in solving a constraint optimization problem using Lagrange's function. Okay, Lagrange's method rather. First, we whatever the constant is given as, we set it equal to 0 and subsequently multiply it by lambda. Okay, then we can form the Lagrange's function. So I will denote L as the Lagrange's function. Okay, our Lagrange's function is the function of capital, labor, and lambda. Okay, so we have three variables. So how do we form? First, we write this objective function. Okay, this Lagrange's function is the aggregate of this objective function and the resulting constraint function, which was formed first setting the constraint equal to 0 and multiplying it by lambda. So we write the objective function, that is k to the power 0.5 l to the power 0.5 plus we add our this resulting constant, that is 368 minus 8k minus 4l. Okay, now we are given this very Lagrange's function. Now the first order condition for this very Lagrange's function, okay, is that we partially, so I will write here, first order condition requires that we take the partial derivative of this very Lagrange's function with respect to capital, labor, and lambda, and set them equal to 0 simultaneously and solve for capital and labor. Okay, so first we will partially differentiate with respect to, let us say, capital. Okay, so L subscript k means partially differentiating this Lagrange's function with respect to capital, which will mean, so we have to differentiate this very capital K here. Okay, by power function rule, this 0.5 will become coefficient, so I will write 0.5 K and exponent is subtracted by 1. This is the power function rule. So 0.5 minus 1 will be minus 0.5. Okay, and we have this L 0.5. Okay, since we are differentiating with respect to capital, so this L 0.5 will remain same. Okay, here we can see, since we are differentiating with respect to k, here the derivative of k is simply 1, so we have minus 8 here, and minus 8 is multiplied with this lambda, so we will get minus 8 lambda. Okay, derivative of constant is 0, and here derivative of L would be 0 because we are differentiating with respect to k partially. Okay, and we set it equal to 0, which implies, if we can write here, 0.5 k to the power minus 0.5 L to the power 0.5, and we transpose this minus 8 lambda on RHS, this will become plus 8 lambda. Okay. Similarly, differentiating partially with respect to L. Okay, so we differentiate this Lagrange function with respect to L. Similarly, this 0.5 will become coefficient, so I will write 0.5. Okay, this exponent is subtracted by 1, so this will become L to the power minus 0.5. Okay, I have written uh, this very term rather here first. Okay, because we know that the multiplication is commutative, we can write multiplication in any order, and then I write this k to the power 0.5. Okay, similarly, since we are differentiating with respect to L, the derivative of L is 1, so we are left with minus 4 into lambda, so this is minus 4 lambda is equal to 0, which implies 0.5 L to the power minus 0.5 k to the power 0.5. Transposing this minus 4 lambda here, this will become plus 4 lambda. Okay, let this be equation first, this be second. Similarly, partially differentiating with respect to lambda now. Okay, so the derivative of lambda is 0 here, no lambda is involved, so it is 0 here, so the derivative of lambda is 1, so we are left with this with we are left, sorry, with this 368 minus 8k minus 4l and set it equal to 0. Okay, now what will we do? Let this be equation third. We divide equation first by equation second, that means dividing equation first by second implies what we are given here. We have 0.5 k to the power minus 0.5 L to the power 0.5, and we divided by this 0.5 L to the power minus 0.5 and k to the power 0.5. Okay, which implies we have 8 lambda divided by 4 lambda. Lambda will get vanished, cancelled. Okay, 4 ones are 4 twos are, so we get here 2. Okay, here 0.5 will get cancelled. Now what will we do here? I will write this very L to the power 0.5, L to the power 0.5, and I will transpose this L to the power minus 0.5 to the numerator. When transposing denominator to the numerator, the exponent the sign of the exponent gets changed. Since it is minus 0.5, it will become plus 0.5. So this is L to the power 0.5. Okay, divided by, similarly we have k to the power 0.5, and I will transpose this numerator on denominator, and again the exponent, the sign of the exponent will change. Since it is minus 0.5, this will become k to the power 0.5, which is equal to 2. Okay, now k L to the power 0.5, L to the power 0.5, bases are same, exponents get added, so it is L to the power 0.5 into 0.5, 0.5 plus 0.5 would be equal to L, sorry, 1, so we are left with L to the power 1. Okay, here we have similarly bases are same, powers are added, exponents are added, 0.5 plus 0.5 is 1, so we don't actually write this one, because when no power is in, when there is 1 as the exponent, then we don't write that very one. Okay, and which is equal to 2. Now we can write L is equal to, transposing here, this will become 2k. Okay, so we put this L is equal to 2k in this very equation, constant in last equation. Okay, to get the value of k or L, whatever we will get. So we put L is equal to 2k in this very equation, so we are with this 368 minus 8k minus 4. The value of L is 2k, so I will write 2k, which is equal to 0, or we can write 368 minus 8k Now 4 2s are 8, this will minus 8k is equal to 0, or 368 minus 16k is equal to 0, or 16k is equal to 368, or k is equal to 368 divided by 16. Okay, now doing the multiplication here, 8 2s are 16, 8 4s are 32. Okay, 4 gets carried, so this will become 48. So 8 6 are 48, so we got here 46 divided by 2. Now 2 2s are 4, 2 3s are 6, which implies the optimal value of k would be 23. Okay, similarly, what will we do? We put k is equal to 23 either in this equation, or in this very equation third, or in this. It is up to you. So we will put this in this very equation. The value of k is equal to 23, so this will become 368 minus 8. The value of k is 23, so I will write 23 minus 4l is equal to 0, or 368 minus 8, 3s are 24. Now 8 2s are 16, 17, 18, so I get 184 minus 4l is equal to 0. Now 368 minus 184, now 8 minus 4 is 4, now 6 minus 8 is 8, 2 minus 1 is 1. Okay, so we get here 184 minus 4l is equal to 0, or 184 is equal to 4l, or 4l is equal to 1. Sorry, I will write directly 184. When transposing this 4, it will become the denominator, now which means l is equal to, now 4 4s are 16, and 17 18, 2 gets carried, so this will be 24. 4 6 are 24, so the value of l is 48. L is equal to 48. That means the level of capital and labor or rather that maximizes utility would be 23 and 48. Okay, I hope I make myself clear in this video. Thank you.